When E is greater than 0, we're dealing with continuum states. And so there's no quantization of energy there. Any amount of energy is allowed. When energy is less than 0, what you'll find if you solve the Schrodinger equation is you're going to find bound states. Okay? Bound states, and you have quantization of energy. And it turns out when you solve this problem, you'll end up with the wave function, and it's convenient to express it in r, theta, and phi. So instead of little x, little y, and little z for the relative coordinates of the reduced mass, we're going to use r, theta, and phi. Okay? Because if you did that, okay, you'll get a simple solution. And that's always the case whenever you have a spherically symmetric problem. You have what's called a central force problem, where the force depends only on the distance from the origin. You have what's called a central force problem. The solution is fairly simple. It's just a function of r times the spherical harmonic. And we've seen this spherical harmonic before. I gave you a heads up on this when we talk about the particle in a sphere. That function shows up again in the solution to the hydrogen atom problem. Okay? So your y, we've seen that before. That's basically the same functions for the particle in a sphere. So your m is an integer that goes from negative L to plus L. We call that the magnetic quantum number. And later in this presentation, we'll learn why it's called a magnetic quantum number. And L, okay, it's a non-negative number, but now remember we said L must be equal to 0, 1, 2, 3, and so on. Now there's now an additional restriction for L. So we now have a three-dimensional problem. In a particle in a sphere, you have two dimensions, theta and phi. You come up with two quantum numbers, L and m sub L, right? L and m. Well, here we have another dimension. We have r, theta, and phi. So we now have three quantum numbers. So a restriction will arise for L. L cannot exceed n. So the maximum value for L is n. And we have a third quantum number, which is n. N is a number that's restricted to positive values. So that means what? Positive integers. 1, 2, 3, 4, and so on. Those are the allowed values of n. And like I said, L must be less than n. Okay? The wave function here is what we call the atomic orbital. It essentially describes the electron. Okay? Describing the reduced mass, which is the electron. Since psi gives us information about probabilities of finding the electron, among other things, okay, there's a lot of information we can get out of psi. One of the most important ones is probabilities of locating the electrons around your nucleus. It's customary to think of the word orbital as like a place for an electron to live in. Like so we talk about electrons occupying an orbital or being in an orbital. Strictly speaking, an orbital is really just a mathematical function that gives you, among other things, information about where you might find the electron. So when we say it's in an orbital, it's an occupying an orbital, what we really mean is it's assigned to this particular mathematical function, wave function.